We're now going to look at the mathematics behind the opener for this week. And a lot of what we're going to look at is actually a review of the end of last week when we talked about projection onto the column space of A. There we used it to solve the linear least squares problem. Now we're going to see how we can use it in order to do data compression. So here we review. We start by looking at the case where we have a vector A and we look at the span of A, and notice that that's the same as looking at the column space of the matrix that has only A as a column. How did this work? Well, if we have a component in the direction of A and we have a component orthogonal to it, then B is equal to Z plus W. That's something we saw in week 1. What we also saw in week 1 was that any vector in the same direction as another vector is just a scaling of that vector. So Z is just some scalar chi times A. W we take to be orthogonal to A. Why? Because that means that this point is the closest point to the point that B points to in the space spanned by A. So what does that mean? We know that A transpose times W is 0. We know how to solve this for W. That gives us this right here. And then we know that Z is just some scalar times A. And if we then multiply all of this out, distributing the dot product as we learned in week 1, we get this right here. And if we then bring this to the other side, what we get is this equation right here, which looks remarkably like the normal equations for the case where the matrix A has only one column. And then we can solve for chi. Because A transpose A is just a scalar, we can just divide both sides by that, or we can write this as the dot product of A with itself inverse times the scalar that results from taking the dot product of A with B. If we then want to know what this vector Z is, that is the projection of B onto the space spanned by the vector A, that's a matter of now taking this solution, chi, multiplying it times A, and then we can rearrange that as such. And the reason why rearranging that as such is important is because then this is the matrix that projects any vector onto the space spanned by the vector A. And then if we want to know what the component orthogonal to that is, we can simply take B minus Z. That's solving this equation here for W. And that's this right here. But since we know that B is just the identity times B, we can take our B, bring it outside, and we end up with a matrix that performs the projection of any vector onto the space orthogonal to the vector A. This is just a review of last week's material. Now we can do exactly the same thing when we're given a matrix A and we ask the question of how to project onto the column space of A. We know that a projection onto the column space of A means that we want to take a linear combination of the columns of A, but taking a linear combination of the columns of A we saw in week 2 is just a matter of doing a matrix vector multiply. So now what we would like to do is determine what that linear combination is that we need to take, what the coefficients are for the linear combination, and that then will give us our vector Z. That's the projection of our vector B onto the column space of A. Here we again write B as Z plus W. We know that Z must be a linear combination of the columns of A. We know that W must be orthogonal to the null space of A transpose. That's what we learned when we looked at the 4 fundamental spaces last week. That then leads to this right here, and that leaves us with this, which we call the normal equation, and then we can multiply both sides by the inverse of the matrix A transpose A, and then we can solve for what the coefficients are for our linear combination, and then we can take the linear combination of the columns of A to give us our vector Z, that is the projection of B onto the column space of A. And finally, if we want to, we can compute W. the vector orthogonal to that space as B minus Z, and if you work it out, this is the matrix that projects onto the space orthogonal to the column space of A. And this is all under the assumption that A actually has linearly independent columns, which we're going to implicitly assume for the rest of this week. Now, I always like to compare and contrast. Here's the case where you had a single vector. Here's the case where you have a matrix where you want to take the linear combination of the columns of that matrix. And if you go back and forth, you can see the similarity. So, given vectors A and B, this is the matrix that projects B onto the span of A, which is also the column space of the matrix that only has A as a column. And then this is the matrix that projects B onto the space orthogonal to the span of A, which is also the null space of A transpose viewed as a matrix.